All right, let's dive into some quantum physics today with this essay by Jorgo Schneppat about a guy named Clinton Davisson. Ever heard of him?
Maybe not, but you've definitely used his work. Smartphones, laptops, even medical imaging. All that stuff relies on understanding the quantum world. And Davisson, he kind of helps open that door way back in the 1920s.
So we're talking foundation of modern tech then.
Exactly. And what's so cool is how his story, it really breaks that whole image of science being, a straight line. Sometimes the biggest discoveries come from the stumbles, the unexpected stuff.
Okay, so paint the picture for me. It's the roaring 20s, jazz is everywhere. But in physics, things are about to get even wilder. All those classical physics rules, like Newton's laws, they worked great for centuries. But zoom down to the level of atoms and things start to break down.
Yeah, scientists were hitting a wall, couldn't explain what they were seeing at that level, like trying to fit square pegs in round holes. And then comes Louis de Broglie, a French physicist. He just drops this bombshell idea. What if electrons, those tiny particles, also acted like waves?
Wait, hold on. How can something be a solid particle A and D, a wave? That's like saying a basketball can ripple like water.
Right. It's mind-boggling. But that was de Broglie's theory. Of course, like any wild scientific idea, he needed proof.
And that's where our guy Clinton Davisson comes in.
Exactly. An American physicist working at Bell Labs. He was an experimentalist, meaning hands-on, build it and see what happens kind of guy.
And lucky for us, Bell Labs was known for letting their scientists chase these big, out there ideas.
Oh, absolutely. And that freedom is crucial to this whole story. Because initially, Davisson wasn't even trying to prove de Broglie's theory. He was just doing his thing, studying how electrons scattered off a nickel crystal.
So just tinkering around in the lab?
Pretty much. And science loves to throw curveballs, because that's when things get interesting.
Okay, I'm hooked. Did he, accidentally invent teleportation or something?
Not quite teleportation, but close in terms of impact, I'd say. So during one experiment, there's this mishap. The nickel gets superheated, its structure changes.
That sounds like it could mess things up.
You'd think so, right? But Davisson, he restarts his experiment, and suddenly the electrons aren't scattering randomly anymore. They're forming a pattern.
A lab accident leads to a major breakthrough. That's wild. What did this pattern look like?
It looked just like you'd see if waves were interfering with each other. Like imagine dropping two pebbles in a pond. You get those ripples intersecting, making those cool patterns. That's wave interference, and that's what Davisson saw. But with electrons.
So those tiny electrons, they were acting like waves. This seems like a huge deal.
Oh, it was monumental. The first experimental proof of de Broglie's wave-particle duality. It wasn't just some crazy theory anymore. It was real, demonstrable. Our whole understanding of matter had to be rethought.
It's like finding out the world is made of Legos.
Yeah.
But these Legos can melt into liquid and then reform.
Exactly. It changes everything. In the scientific world, they went nuts, understandably. Davisson and his colleague, Lester Germer, they published their findings. And in 1937, they win the Nobel Prize in Physics.
Well deserved, for sure. But like Schneppat points out in his essay, this went way beyond just a prize. This was a fundamental shift in how we see the universe.
Absolutely, and that's where things get really interesting.
So what were the immediate ripple effects of this discovery? How did this theoretical leap lead to stuff we actually use today?
Well, for one, understanding electrons as waves led to the electron microscope. Think super-powered microscope. You can see things thousands of times smaller than with regular light microscopes. We're talking seeing individual atoms.
Wow, that's incredible. And I know electron microscopes are used in so many fields now.
It's like seeing a whole universe inside a drop of water. Revolutionized material science, biology, medicine, a whole new way of looking at the world.
It's amazing how something as abstract as wave-particle duality can have such a practical impact.
And it goes even further than that. Understanding electrons as waves also led to the development of semiconductors and transistors, the tiny components at the heart of all modern electronics.
Hold on, are you saying my phone exists because of this?
Exactly. It's mind-blowing how research that started with pure curiosity could have such a huge impact.
And to think, it all started with a little lab accident.
It just goes to show, sometimes the most important breakthroughs happen when you least expect them.
It makes you wonder what other mysteries are out there just waiting to be discovered.
Oh, there are countless mysteries still hidden in the quantum world. And who knows, maybe one day, our listeners, their curiosity will lead to the next big breakthrough.
Now that's a thought to hold on to. Thanks for diving into this with me. Until next time, keep exploring, keep questioning, and stay curious about the world around you.
Think of it this way. A normal computer, it uses bits, which are like tiny switches. They can be on or off, representing a 1 or a 0, but a quantum computer uses qubits, and those are like these weird quantum particles that can be both on and off at the same time.
Whoa, hold on. So a qubit can be a 1, a 0, or both at the same time.
Exactly. That's the weirdness of quantum mechanics.
So it can hold way more information than a regular bit.
You got it! And because of that, quantum computers can solve problems that would take a classical computer, like billions of years.
Okay, that's insane. What kind of problems are we talking about?
Designing new drugs, creating new materials, breaking unbreakable codes. We're still early, but quantum computing could change everything.
It's like Davisson opened this door to a whole new realm of possibilities. We're just starting to peek inside.
And it all goes back to those insights about the quantum world he helped uncover.
Okay, before we get too lost in the future, let's go back to the electron microscope. How does it actually work? I get that it lets us see tiny stuff, but what's the connection to wave-particle duality?
Okay, so imagine you're trying to look at a virus, something super tiny. With a regular microscope, you shine light on it, and that light bounces back to your eye. But with objects that small, the light waves are just too big. It's like trying to feel a grain of sand with boxing gloves on.
Right, you need a smaller tool, something that can actually interact with those tiny structures.
Exactly. And that's where electrons come in. Remember, Davisson showed us they can act like waves, so instead of light, we use a beam of electrons. They have much smaller wavelengths, so we can see things in much finer detail.
So basically replacing light with electrons. Pretty clever.
It is. And this ability to see at the nanoscale, thanks to Davisson, has revolutionized so many fields. Material science, for example. Now we can examine the structure of materials in incredible detail, leading to stronger, lighter materials.
So that's why we have things like ultralight carbon fiber and stuff.
Exactly. Or in medicine, we can study viruses and bacteria up close. Helps us understand how they work, how to fight them.
It's like having a superpower, seeing this invisible world all around us.
And it's not just about seeing smaller. It's about understanding the fundamental properties of materials. For example, semiconductor technology. The whole industry relies on controlling electrons at the atomic level.
Okay, let's talk semiconductors. They're the heart of our electronics, but I'll admit I'm a bit fuzzy on how they work.
Sure, semiconductors are kind of in between. Not great conductors like copper, but not insulators like rubber either. We can control their conductivity, which makes them perfect for electronics.
So how does this all tie back to Davisson and electron waves?
This is where it gets really cool. So how electrons behave inside a semiconductor, it actually depends on their wave-like properties. Remember how those waves can interfere, create patterns? Well, in a semiconductor, those patterns create areas where electrons are more likely to be and areas where they're less likely.
Interesting.
We call these areas energy bands.
So it's like electrons are zipping around and their wave behavior creates these zones where they can hang out.
Exactly. And the cool part is, we can manipulate these energy bands, which lets us control the flow of electricity really precisely.
So it's all about manipulating those electron waves. Mind blown.
And that's the basis of transistors, the building blocks of computers, phones, everything. By controlling the energy bands, a transistor becomes like a tiny switch, turning electricity on or off.
And these tiny switches let our devices process information.
Precisely.
So from a lab experiment with electrons scattering to the transistors that power our world, it's all connected.
It really is. It shows the power of fundamental research, just following curiosity.
Makes you wonder what other breakthroughs are just waiting to be found.
Oh, I'm sure there are many more out there, just waiting for someone to uncover them.
And it makes you wonder what else is out there, like quantum communication. It's another one of those futuristic things you hear about all the time these days.
Yeah, it's pretty wild.
What makes it so special?
Basically, quantum communication uses those bizarre quantum properties to create like super secure channels. In theory, completely unhackable.
Unhackable? That sounds like something out of a spy movie.
It's all thanks to this thing called entanglement. It's where two particles, they get linked, they share the same fate no matter how far apart they are.
So like an invisible connection that ignores distance.
Exactly. So imagine using these entangled particles to send information. Now, if someone tries to snoop, they mess with the entanglement. And that instantly alerts both the sender and the receiver.
So it's like a self-destructing message.
Pretty much. It's a security system built into the laws of physics.
That's incredible. So this is actually real, not just theoretical.
Oh, it's real. And it all comes back to those early discoveries in quantum mechanics. People like Davisson, they laid the groundwork.
It's amazing to think how his work back then is shaping the future. Going back to that essay by Yurgo Schneepat, Clinton Joseph, he might not be a famous name, but his work has had this huge impact. We wouldn't have the technology we use today without him.
He really paved the way for so much.
And it all started with him just trying to understand how electrons bounce around.
It's a testament to the power of curiosity.
It makes you wonder what other mysteries are still out there in the quantum world and beyond.
I'm sure there's plenty more to discover.
Well, that's a great thought to wrap things up on. Thanks for joining us on this deep dive into the world of Clinton Davisson and quantum physics. Until next time, keep exploring, keep questioning, and stay curious.